A recent experiment in quantum mechanics has shocked scientists. Previously, in all quantum experiments, the observer was considered a fixed entity, separate from the system being observed. But a new study has revealed something incredible. The observer itself can also exist in a superposition of states, just like the particle it is observing. This new idea is called the quantum reference frame theory. When scientists reran previous quantum experiments using this new approach, they discovered that reality is even weirder than we ever imagined. This breakthrough might finally help solve some of the biggest paradoxes about reality. To understand this better, let's explore this new theory in depth and see how it shocks scientists by revealing some bizarre and unexpected nature of reality. Inside every atom, the tiny particles that make up our world don't behave the way we expect from everyday experience. Scientists have spent decades studying electrons, and they've discovered something astonishing. An electron doesn't have a fixed position like a planet orbiting a star. Instead, it exists in a cloud of possibilities, meaning it could be anywhere around the nucleus at any given moment. But here's where it gets even stranger. The moment you try to observe or measure the electron's position, all those possibilities disappear, and the electron chooses a single location. This is exactly like the magical room. Before you open the door, every possibility exists. But the act of observing forces the room, or in this case the electron, to settle into just one outcome. It suggests that reality at its most fundamental level isn't set in stone. It's shaped by observation and interaction. But when Einstein learned about this strange nature of the quantum world, he was stunned. Einstein was skeptical about quantum theory, especially its idea that events at the smallest scales are governed by probability rather than certainty. He famously said, "God does not play dice," expressing his belief that the universe should follow clear deterministic rules rather than randomness. In other words, he thought that if we fully understood the laws of physics, we should be able to predict every event precisely without relying on chance. However, modern physics has shown that quantum mechanics is fundamentally probabilistic, meaning that at a microscopic level, nature does involve randomness, and we can only predict the likelihood of events rather than their exact outcomes. To challenge quantum mechanics, Einstein pointed out several paradoxes, situations where the predictions of the theory seem to contradict common sense or fundamental principles of physics. One of the most famous paradoxes he revealed was the EPR paradox, named after a 1935 paper he co-wrote with physicists Boris Podolsky and Nathan Rosen. In the EPR paper, Einstein and his colleagues revealed about a strange phenomenon called entanglement. When two particles become entangled, their properties remain connected no matter how far apart they are. If you measure one particle, the other particle's state seems to be instantly determined even if they are light years away from each other. Einstein found this deeply troubling. He argued that this kind of instant connection violated the principle that no information can travel faster than the speed of light, as stated in his theory of relativity. Einstein and his colleagues argued that if quantum mechanics was correct, then either information is somehow traveling faster than light, which would break the laws of physics, or the particles must have hidden information that predetermined their states before they are measured. Einstein favored the second explanation because he believed that physics should be deterministic, meaning that everything should have a definite cause and outcome. He thought that quantum mechanics was incomplete and that a deeper theory, one that included these hidden variables, would eventually explain reality in a more logical and predictable way. For many years, physicists debated whether Einstein was correct in thinking that quantum mechanics was incomplete. However, in the 1960s, physicist John Bell proposed Bell's theorem, which provided a way to test whether hidden variables could explain quantum mechanics. Later experiments particularly in the 1980s and beyond, confirmed that Einstein was mistaken. Quantum entanglement is real, and no hidden variables can fully account for its effects. Also, the Copenhagen interpretation says that, before we observe a quantum particle, it doesn't have a fixed state. Instead, it exists in superposition, meaning it is in all possible states at once. But when we measure it, this uncertainty disappears, and the particle instantly settles into one definite state. This process is called wave function collapse. In simple terms, this means that our act of observing or measuring something actually shapes the reality we see. Even though Einstein was eventually proven wrong, he strongly disagreed with the Copenhagen interpretation, especially the idea that reality depends on observation. He argued that it was too strange and incomplete to say that something only becomes real when we measure it. Interestingly, around the same time, another famous physicist, Erwin Schrodinger, also found this idea unsettling. To highlight its problems, he came up with a famous thought experiment called Schrodinger's cat, which imagined a cat inside a box that could be both alive and dead at the same time until someone looked inside. Imagine a cat is placed inside a box with a radioactive atom, a Geiger counter which detects radiation, a poison bottle, and a hammer. If the radioactive atom decays, the Geiger counter detects it, triggering the hammer to break the poison bottle which kills the cat, and if the atom does not decay, the cat remains alive. According to the Copenhagen interpretation, the radioactive atom is in a superposition. It is both decayed and not decayed until measured. And the cat should also be in a superposition of both alive and dead at the same time until someone opens the box and observes it. But physicist Erwin Schrodinger raised an important question. Like, what counts as an observer? Does the cat itself observe the atom's decay? If the cat can already observe the event, then the wave function collapse happens before a human looks, making superposition meaningless in this case, and the cat is either alive or dead before we look. Or does wave function collapse only happen when a human opens the box? If that's true, then the cat really is both alive and dead at the same time, which doesn't make sense in our everyday experience. Einstein was deeply impressed by Schrodinger's thought experiment and even wrote him a letter in which he expressed his thoughts on it, saying, "You are the only contemporary physicist besides Laue who sees that one cannot get around the assumption of reality if only one is honest. Most of them simply do not see what sort of risky game they are playing with reality as something independent of what is experimentally established. Nobody really doubts that the presence or absence of the cat is something independent of the act of observation." Schrodinger's famous thought experiment with the cat actually supports Einstein's skepticism about the role of an observer in quantum mechanics. Einstein questioned whether reality truly depends on an observer or a measurement to exist. Even today, scientists are still trying to understand what actually causes the wave function to collapse. The mystery remains unsolved, and some of the greatest minds in physics continue to debate it. Even Nobel Prize-winning physicist Dr. Roger Penrose believes that conscious observation or simple measurement does not cause the wave function to collapse.
What collapses the wave function is physics. So there is something in physics which collapses the wave function. The Schrodinger equation, quantum theory as a whole, is wrong. It's not Einstein was wrong. Quantum mechanics is wrong. Now, I say this very blatantly because it's a blatant topic. I mean, Einstein and Schrodinger were much more polite. They said it was incomplete.
Well, over the years, scientists have proposed several other theories to explain the superposition of particles and the collapse of those states. One of the most famous interpretations is the many worlds interpretation. It is slightly different from the Copenhagen interpretation. In Copenhagen, the cat is in superposition until an observer opens the box, and the moment an observer looks inside, the act of measurement forces reality to settle into a single, definite outcome. But in many world interpretation, when the box is opened, the universe splits into two. In one branch, the observer sees the cat alive. In another branch, the observer sees the cat dead. Here the wave function never collapses. Instead of choosing one reality, the universe splits into multiple parallel realities, with each possible outcome happening in its own branch. According to this interpretation, the observer is not special. They also split into multiple versions along with the universe. Well, some other interpretation revealed that two different observers see different realities, and that there is no such thing as objective reality. Back in 1961, the Nobel Prize-winning physicist Eugene Wigner outlined a thought experiment that demonstrated how the strange nature of the universe allows two observers to experience different realities. In other words, according to our best theory of the building blocks of nature itself, facts can actually be subjective. If facts can be subjective at the quantum level, then reality itself might not be an absolute fixed entity. Instead, it could depend on the observer's perspective and their relationship to the system they are measuring. At first, this might seem bizarre. After all, in our everyday world, facts appear fixed. A tree exists whether or not someone looks at it. Each of these interpretations tries to explain the strange nature of reality, but they also have weaknesses that prevent them from being universally accepted. Like, Copenhagen interpretation says that reality is objective but depends on the observer, but it does not clearly explain what counts as an observer or why observation causes wave function collapse. The many worlds interpretation argues that all possible realities exist simultaneously, and each choice or observation creates a new branching universe. But if all possible outcomes happen in separate universes, why do we still follow probability rules in quantum mechanics? Some other interpretations suggest that reality is not objective at all. Instead, reality is different for each observer, meaning that what is real depends on the perspective of the observer rather than a single absolute truth. But if reality is different for each observer, then how do observers agree on objective facts? After exploring these theories and paradoxes, we are left with some fundamental questions that still have no clear answers. Well, tighten your seatbelt, because in a recent study, scientists uncovered a new understanding of the quantum world, revealing something so strange about reality that will shake your foundations. A groundbreaking experiment suggests that even the reference frames of observers, the perspectives from which they view quantum events, can exist in a state of superposition. This means that an observer's position may not be definite, but could be spread across multiple possibilities. The findings have major consequences for our understanding of reality. In the Schrödinger's cat experiment, it's not just the cat that exists in a superposition of being both alive and dead. The observer can also be in multiple superposed states. Before diving into the quantum world, let's understand a simple concept, a reference frame. Imagine you are sitting in a moving train. If you look at someone sitting next to you, they appear still, but to an observer standing outside, both of you are moving at the train's speed. This difference in perspective is because of reference frames, different points of view from which motion and positions are measured. In classical physics, reference frames are straightforward. A moving car has its own reference frame, and a person standing on the road has a different reference frame. But in quantum mechanics, reference frames become weird because objects can exist in superposition, meaning they can be in two places at the same time. To understand this, imagine two observers, A and B, each using a different reference point to describe the world. Normally, we think of one observer as stationary and the other moving, but in the quantum world things get weird. Suppose A is attached to a tiny quantum object that has a probability of being in multiple places at once. Another observer, B, is a separate observer watching A. According to quantum reference frame theory, From the perspective of another observer B, the observer A is not at a single definite position, but is spread out in a quantum superposition just like the particle. So, if observer A performs a measurement, their result might not match what observer B sees, because B sees A in a superposition. Surprisingly, from A's perspective, it is B who appears to be in superposition. This means that superposition is not an absolute property, it is relative. What looks like superposition from one observer's reference frame may not look the same from another's. Well, it resolves some of the major paradoxes in quantum mechanics, such as when Schrodinger questioned the idea of superposition by asking, "Does the cat inside the box already know whether the radioactive decay happened?" If the cat can observe its own fate, then from the cat's perspective, there is no superposition. It either lives or dies based on the decay. No previous interpretation of quantum mechanics fully answered this question. But according to quantum reference frame theory, the cat inside the box does not have a fixed reality either. From the cat's point of view, the observer outside the box is in a superposition of two states, one where they see a dead cat and one where they see a living cat. This means that superposition is not just about the cat, it also applies to the observer depending on the perspective taken. Instead of having a single objective reality, quantum reference frame theory suggests that reality shifts depending on who is observing and from where. This changes our entire understanding of what it means for something to be real. Now, let's make things even stranger. What if B is also anchored to a quantum object that's in a superposition of two locations? Then A's quantum state is now smeared out in two different ways depending on the possible locations of B. Because determining B's quantum state determines A's state, here we can say that A and B are now entangled. This reveals that even entanglement is relative. The properties of quantum systems are not absolute, but depend on who is measuring and from which frame of reference. This challenges our classical idea that entanglement is a fixed absolute relationship between two particles. Instead, entanglement is itself observer-dependent. Quantum reference frame theory changes how we think about reality by suggesting that even the observer is in a superposition. It says that what we see as reality depends on our own quantum state. This means that two different observers in different quantum states might experience different versions of reality. Unlike the Copenhagen interpretation, which says reality is objective but depends on measurement, or the many worlds interpretation, which says all possible realities exist in parallel, quantum reference frame theory suggests that there is no single, absolute reality, only different perspectives based on the observer's quantum state. This idea also solves major paradoxes in quantum mechanics. If the cat is in superposition and the observer is also in superposition, then from the cat's point of view, the observer is in multiple states as well. This removes the need for wave function collapse, which is one of the biggest mysteries in quantum mechanics. Instead of collapsing, reality just shifts depending on the observer's quantum state. This theory could even help bridge the gap between quantum mechanics and relativity, offering a new way to understand space, time, and the very nature of existence. What if I say there is a super observer who observes everything in the universe? Imagine someone watching everything that happens in the entire universe all the time. It sounds like something out of a sci-fi movie, right? Well, in the fascinating world of quantum physics, a new experiment has sparked excitement by hinting at the existence of such an observer. Scientists conducting a quantum experiment stumbled upon something unexpected. They found clues that suggest there might be an ultimate observer, or perhaps a form of cosmic surveillance, watching over every particle and event in the universe. This experiment was conducted by theoretical physicists from Princeton University. In this quantum experiment, they found that there is something at the very edge of our observable universe that observes everything in the universe. Well, to understand this fascinating experiment, we need to know some basics about how observation affects reality. And if there truly is an observer overseeing everything, it implies that consciousness or awareness plays a fundamental role in the fabric of the universe itself. According to the prevailing cosmological model known as the Big Bang Theory, the universe began as a hot, dense state approximately 13.8 billion years ago and has been expanding and evolving ever since. This model provides a scientific framework for understanding the universe's existence without invoking the need for an external observer. But quantum mechanics, in particular, challenges our understanding of causality and the relationship between observer and observed. According to the Copenhagen interpretation, an electron around an atom can exist in different positions simultaneously before measurement, but when the measurement occurs, all possible existences converge into a definite reality. The act of observation plays a fundamental role in shaping reality at the quantum level. In this view, the universe requires an ultimate observer to give it meaning and substance. And more surprisingly, theoretical physicist Gautam Satishchandran of Princeton University, along with theoretical physicists Dane Danielson and Robert Wald, both of the University of Chicago, recently conducted a quantum thought experiment near a black hole. They found that the black hole actually behaves like an observer. First, the team imagined a person, call her Alice, performing the famous double-slit experiment in a lab orbiting a black hole. As you guys already know, in the case of double-slit experiment, scientists sends a particle, like an electron or a photon, toward a pair of slits in a solid barrier. If no one observes the particle's progress, an interference pattern typical of waves appears on a screen on the other side of the barrier, as if the particle went through both slits at once. But if someone, or some device, measures the particle's path, it will register as having gone through one slit or the other. The particle's quantum state of apparently being in two places at once collapses. But here's a twist. Scientists added another person named Bob is sitting just inside the black hole's event horizon. This event horizon is like a boundary beyond which even light cannot escape the black hole's gravity. Even though Bob is doomed, he can still make measurements. Well, when Bob, sitting inside the black hole, observes which slit Alice's particle passed through, the quantum state of the particle will suddenly collapse. And this would also let Alice know Bob is there, messing up her experiment. But that's a paradox. Nothing done inside a black hole should affect the outside. By the laws of physics, Bob should not be able to communicate with Alice at all. Yet by observing the collapse state of the wave function, Alice knows that Bob was observing the path of the electrons. How is this possible? Black holes are a one-way street. Nothing done in the interior of a black hole can affect Alice's experiment that he does in the exterior. But we just made up a scenario in which definitely the experiment will be affected. The team then guessed at a possible solution to this paradox. They said the black hole itself forces the quantum state of Alice's particle to collapse, whether Bob is there or not. Theoretical physicist Satishchandran says, the event horizon of the black hole actually knows which way the particle went. Alice blames the black hole for ruining her experiment, not Bob, and the paradox is resolved. Scientists argue that there is something unique and insidious about such horizon effects. Usually, physicists can create an isolated superposition states by shielding their experiment from the external environment. A vacuum, for example, prevents the superposition from collapsing by removing the influence of surrounding gas molecules. But nothing can shield gravity, so there is no way to protect an experiment from the long-range effects of gravity. Eventually, every superposition will collapse completely due to the presence of a black hole horizon. But the team discovered something even more astonishing. It's not just about black hole event horizons. Anywhere there's a horizon that lets information move in only one direction, quantum superposition collapses. That means even the edge of our observable universe can play the role of an observer. The cosmic horizon, much like the event horizon of a black hole, only allows information to go one way. So, in a way, our universe's horizon acts like an observer too. It seems as if the universe is watching everything, to make sure the particles aren't having a cosmic party instead of doing their job properly. But what does it really mean that the universe is watching everything? At Princeton University in the early 1970s, the celebrated theoretical physicist John Wheeler could be spotted in seminars' hallway discussions drawing a big U. The letter's left tip represented the beginning of the universe, where everything was uncertain and all quantum possibilities were happening at the same time. The letter's right tip, sometimes adorned with an eye, depicted an observer looking back in time, thus bringing the left side of the U into existence. Wheeler called it participatory universe. In this participatory universe, the cosmos expanded and cooled around the U, forming structures and eventually creating observers like humans and measuring apparatus. And by looking back to the early universe, these observers somehow made it real. Scientists argued that this recent quantum experiment near a black hole has made Wheeler's concept of a participatory universe even clearer. One of the researchers, Dane Danielson, said, "The finding that black holes and killing horizon of our universe observe everything all the time, whether you like it or not, is more evocative of the participatory universe." From all these things, we come to the conclusion that the universe is the ultimate observer who observes everything that happens inside it. We cannot hide anything from the universe. Well, this possibility raises a big question that the universe can be a conscious being. There are many scientific theories that suggest that the whole universe can be a giant conscious brain. The idea that our universe might be conscious and observing opens up a realm of possibilities and challenges our preconceived notions about the nature of reality. As we gaze up at the night sky, let us remember that the universe itself acts as an ultimate observer to shape the reality. And we are not merely passive observers of the universe, but active participants in its unfolding story. Whether or not it's true remains an open question, but the journey of exploration is itself a source of inspiration and wonder. And who knows? Perhaps one day we'll unlock the secrets of the cosmic mind and glimpse the true nature of our living universe. A major announcement about alien life is on the way. Two teams of scientists from China and America have made an exciting discovery that they believe could be the first ever message from an extraterrestrial civilization. But what exactly did they find? And why do they think it could be a message from aliens? In this video, we'll break down this incredible discovery. Get ready to be amazed. It all started in 2019. It was a quiet day at the Parkes Observatory in Australia, one of the most important sites in the world for scanning the skies. This enormous radio telescope, also known as the Dish, had been a key player in the search for extraterrestrial intelligence for years. Scientists from all over the world used it to listen for faint radio signals from deep space, hoping to catch a glimpse, or rather, a sound of alien life. On that particular day, the telescope picked up something unusual. A strange signal was detected, something unlike the typical noises of space. This mysterious signal was named BLC-1, short for Breakthrough Listen Candidate 1, as it was the first strong candidate for further investigation by the project. Excitement began to grow among the team. What if this was the signal they had been hoping for all these years? What if BLC-1 was proof of an advanced alien civilization trying to communicate with Earth? The idea was thrilling but also required careful investigation. Proxima Centauri is a fascinating star system for another reason too. It has at least 2 planets orbiting around it, one of which, called Proxima b, is in the habitable zone. This means that it's at just the right distance from the star where liquid water could exist, making it a potential place for life. So when scientists found that BLC-1 appeared to come from this system, they couldn't help but wonder if it could be connected to life on Proxima b. But detecting such a signal wasn't enough to jump to conclusions. For decades, astronomers had been looking for signs of intelligent life beyond Earth, and many mysterious signals had turned out to be false alarms. Often, these signals were caused by interference from human-made sources like satellites, aircraft, or other electronic devices. Could BLC-1 be one of these? At first, this signal didn't match any known human-made signals. It had a narrow band frequency, which is something typically associated with technology rather than natural cosmic events. It also lasted for several hours and appeared to disappear when the telescope moved away from Proxima Centauri, making it seem like it was truly coming from that direction. Everything about it seemed so promising. Was it possible that we were finally on the verge of confirming the existence of intelligent alien life? Excitement around this mysterious signal continued to grow as scientists dug deeper into the data. For months, they worked tirelessly, analyzing the signal, looking for clues and trying to understand what could have caused it. However, as they dug deeper, they realized that things weren't adding up. First, they couldn't find any repeated signals. If BLC-1 were a real message from aliens, you'd expect the signal to show up again in the same way. But after months of observations, BLC-1 never reappeared. This was a major red flag. Real extraterrestrial signals like the ones we send out into space usually repeat or follow a pattern. The fact that BLC-1 didn't come back suggested that it might not be an intentional signal at all. Next, they looked even more closely at the frequency of the signal and how it behaved over time. What they found was disappointing. BLC-1 had small drifts in frequency that looked suspiciously like radio interference from human-made technology. This kind of drift happens when something moves or changes slightly, like a piece of equipment shifting or a signal bouncing off an object. In other words, it didn't seem like something from deep space. Finally, in early 2021, after much anticipation, the scientists made an official statement and revealed that BLC-1 was almost certainly not from aliens. The signal was likely caused by human-made radio interference, possibly from some unknown source near the observatory or from equipment used during the observations. In the case of BLC-1, it seems the signal was produced by a human source, but it was still unclear exactly which piece of equipment was responsible. What was certain, though, was that this wasn't the long-awaited message from an alien civilization. But wait, there is a new twist in this search. Recently, 2 research groups have again found something very strange about this mysterious signal. After months of further analysis, they discovered patterns within the original data that they hadn't seen before. These new findings have caused a stir in the scientific community. In mid-2024, 2 separate research groups, one from the United States and another from China, made headlines by announcing that they had reanalyzed the BLC-1 data and found something surprising. Using new analytical techniques, these teams identified subtle variations in the signal that had gone unnoticed during the initial investigation. These variations were too structured, too precise, to be the result of mere interference. Both groups, working independently, reached the same conclusion that BLC-1 might not be interference after all. The signal's behavior was unlike anything that could be explained by natural or human-made sources. Instead, the new findings pointed to the possibility that BLC-1 could be an artificial signal, one deliberately sent by an intelligent civilization. The implications of this discovery are enormous. If these new analyses are correct, BLC-1 could represent the first concrete evidence of extraterrestrial intelligence. The signal's complexity and persistence suggest that it might be a form of communication, possibly from a civilization orbiting Proxima Centauri. Following this announcement, a race has begun between the two research groups to publish their findings and claim the historic discovery. The American team, working closely with the Breakthrough Listen project, has access to vast resources and cutting-edge technology. Meanwhile, the Chinese group is working with the 500-meter aperture spherical telescope, the largest radio telescope in the world, which provides them with unparalleled observational capabilities. The coordinates of the target object are thought to be known to the Chinese team, and both groups are racing to be the first to make the epical announcement. Professor Simon Holland, an academic involved in SETI research, has hinted that the Chinese team might be pipping the Americans to the post, as both groups rush to release their data and make the world-changing announcement. The stakes could not be higher. If confirmed, the discovery of BLC-1 as an extraterrestrial signal would be the most significant scientific breakthrough in human history. Humanity would no longer be alone in the universe. The discovery would fundamentally alter our understanding of life, intelligence, and the cosmos. It could also raise new questions. What are these beings trying to tell us? Are they aware of our existence? What might their civilization look like? Of course, skepticism remains. Despite the compelling new evidence, many scientists urge caution. But Simon emphasizes, regardless of what the source of BLC-1 signals turns out to be, it's unlike any known natural phenomenon. It's a single point source, and it's not just noise. They argue that more observations are needed to confirm the signal's origin, and that we must avoid jumping to conclusions too quickly. False positives have occurred before, and the scientific method demands thorough verification before any groundbreaking claims are made. Still, the possibility that we might finally have found evidence of non-human intelligence is enough to spark the imaginations of scientists and the general public alike. The search for extraterrestrial life, which once seemed like a distant dream, now feels closer than ever.
As humanity expands its exploration into the vast reaches of the cosmos, uncovering clues about numerous worlds, an ancient question has haunted us for centuries. Is anybody out there? Our Earth is remarkably one of the best places to support life in our solar system, and the diversity we see in Earth's life is incredible. Our universe is unimaginably large, and the possibility of life outside Earth is also very high. Many scientists believe that our universe is teeming with alien life. Well, to find the answer, we look for worlds similar to ours. In our quest to discover life on other planets, we typically focus on finding life forms similar to what we know on Earth. This includes carbon-based life that thrives in the presence of liquid water and depends on light or chemicals for energy. Carbon is the backbone of every known biological molecule. Life on Earth is based on carbon, likely because each carbon atom can form bonds with up to 4 other atoms simultaneously. This quality makes carbon well suited to form the long chains of molecules that serve as the basis for life as we know it, such as proteins and DNA. Although this approach of finding similar life forms is logical when examining Earth-like planets, such as Mars, but a question arises. Does this apply to celestial bodies beyond our solar system? So far, we have only talked about worlds orbiting stars or planets. What about rogue planets, which wander through the universe unattached to any star? They might use thermal energy instead of stellar radiation as a main energy source. Considering these possibilities, scientists have been wondering for some time whether life beyond Earth might be based on chemicals different from those we know here. For example, instead of using water like we do, aliens may use substances like ammonia or methane. And instead of carbon, which forms the building blocks of life on Earth, they could use silicon. These amazing ideas has given rise to other possible life forms other than carbon that could exist in our universe. So let us understand the possible forms of life present in our universe one by one. Scientists have long speculated about the possibility of alternative biochemistry, with silicon-based life being one of the most interesting concepts. Silicon, found abundantly in the Earth's crust, shares some chemical properties with carbon. Silicon, located just below carbon in the periodic table, has some similarities with its elemental neighbor. Both elements can form stable bonds with 4 other atoms, which is important for the formation of complex and diverse molecular structures. In fact, silicon has the ability to form long chains and complex 3-dimensional networks, similar to the carbon-based structures that form the basis of life on Earth. Silicon-based organisms might employ silicon-oxygen polymers as their equivalent of DNA and RNA, and silicate minerals could play roles analogous to carbohydrates and proteins in carbon-based life. One of the most compelling scenarios for silicon-based life involves extreme environments where carbon-based organisms would struggle to survive. For example, environments with high temperatures, acidic conditions, or excessive radiation levels may favor silicon-based biochemistry. Silicon's ability to withstand harsh conditions may make it a viable candidate for life forms on celestial bodies with extreme environments, such as some exoplanets or moons in our own solar system. Imagine a world that's quite different from Earth. A good example in our own solar system is Saturn's moon, Titan. Unlike Earth, it doesn't have oxygen or liquid water. It's incredibly cold, which could actually be suitable for life forms based on something called silanes. However, on Titan, life would need a different liquid to replace water. Titan has lakes made of liquid methane and ethane, which might be the key. However, silicon-based life also presents significant challenges. Unlike carbon, silicon is larger and less flexible in forming different types of chemical bonds. This rigidity may hinder the versatility needed for the wide variety of chemical reactions necessary for life processes. Additionally, silicon-based compounds are less stable in aquatic environments than their carbon-based counterparts, which can create difficulties in maintaining biological systems. Scientists believe the universe may be filled with ammonia-based life instead of carbon, because ammonia can play an important role in maintaining biological life in the absence of liquid water. But scientists have also said that ammonia-based life cannot survive on land. Ammonia, a compound made up of nitrogen and hydrogen atoms, has been proposed as a potential substitute for water in environments where extreme cold temperatures prevail. This speculative concept opens a window into the possibility of radically different forms of life evolving in the far reaches of our universe. One of the key factors driving the consideration of ammonia as a solvent for life is its behavior in extremely low temperatures. On celestial bodies with cold conditions, where water exists primarily in the form of ice, ammonia remains liquid and thus provides a potential habitat for life forms to flourish. In an environment where water and ammonia coexist, the two solvents can interact, creating a mixture that could provide a suitable habitat for life. Such environments may serve as transitional zones, where life forms may employ a combination of biochemical processes based on both ammonia and water chemistry. Ammonia-based life forms might employ nitrogen-based polymers as their equivalent of DNA and RNA, with nitrogenous bases playing the role of genetic information carriers. Proteins, essential for various cellular functions, might be constructed from nitrogen-rich amino acids. The moons of the giant planets such as Jupiter, Saturn, and Uranus, with their sub-zero temperatures, have long been the focus of investigation regarding the possibility of ammonia-based life. Well, ammonia offers interesting possibilities as an alternative solvent, but it also presents significant challenges. For example, ammonia's high reactivity with many substances raises questions about the long-term survival of ammonia-based life forms. Additionally, the biochemistry of ammonia-based life may require unique adaptations due to the limited availability of certain essential elements in ammonia-rich environments. Well, so far, we have seen how elements other than carbon can host life in the universe, but what if life beyond Earth turns out to be completely different from what our theories predict? Life on Earth relies on two special molecules, DNA and RNA, which carry important information. Scientists have always wondered if there could be other molecules like them. While any long chain of molecules can store information, DNA and RNA have a unique ability to pass down genetic traits and adapt over time through evolution. In 2012, a team of scientists from England, Belgium, and Denmark became the first in the world to develop xenonucleic acid, XNA, synthetic nucleotides functionally and structurally similar to DNA and RNA. The team created synthetic polymerases to create 6 new genetic systems: HNA, CNA, LNA, ANA, FANA, and TNA. One of the new genetic systems, HNA or hexatyl nucleic acid, was found to be robust enough to store enough genetic information to serve as the basis for biological systems. This prompts the intriguing possibility that, elsewhere in the vastness of the universe, life forms may exist without DNA and RNA as their genetic basis. Instead, they could rely on entirely different molecules for carrying genetic information. This concept challenges our conventional understanding of life as we know it. Imagine a distant planet where beings are fundamentally distinct, yet equally complex and adapted to their unique environment. Expanding on this, researchers are actively exploring the potential for alternative biochemistries. Some scientists have proposed the idea of shadow life, which refers to hypothetical organisms that could exist on Earth, utilizing unconventional biochemical pathways. These organisms might coexist with familiar life forms, but operate on an entirely different set of molecular principles. In theoretical discussions about plasma-based life, scientists contemplate a biochemistry that operates at energy levels far beyond those encountered on Earth. Instead of relying on the complex organic molecules and water-based reactions that characterize carbon-based life, plasma-based organisms might utilize the charged particles and high-energy interactions of plasma as the basis for their biochemistry. Plasma is a high-energy state of matter, distinct from solids, liquids, and gases. It consists of charged particles, such as ions and free electrons, making it an incredibly energetic and reactive environment. In a paper written in 2007, scientists have generated these ordinary matter plasma cells in the laboratory. Scientists argues that, similar to biological cells, the electrical boundary of these self-assembled gaseous plasma cells provides an enclosed internal environment that differs from the external environment. The cell is able to replicate, by division, and to emit and receive information like DNA and RNA. Research team believes that the plasma cell is potentially able to perform a further biochemical evolution into a living cell. This research has revealed the possibility of a strange life form that may exist in our universe. Highly energetic environments, like the outer atmospheres of stars, might support plasma-based life forms. These would be radically different from life as we know it. An energy being is an alleged life form that is composed of energy rather than matter. Well, this form of life is completely hypothetical right now, but most scientists believe that the universe can support these types of life forms, and that these life forms could be the most advanced civilizations in our universe. If you've delved into the realms of science fiction, you've likely encountered the concept of energy beings. Unlike traditional extraterrestrial creatures, these entities lack physical forms, existing purely as manifestations of energy. They possess the ability to move freely across the cosmos and often exhibit extraordinary powers commensurate with their highly evolved state. They are also typically portrayed as more powerful, more enlightened, and possessing a deeper understanding of the universe. It's almost a given in most science fiction that sufficiently advanced civilizations will eventually develop this way. Converting themselves into beings of pure energy seems like the ultimate stage in the development of any civilization.